Hi, everybody. Thank you for coming to my talk today. It's a bit early, so I appreciate your attendance. My name is Itzik Kotler, Isaac for the most part, and I will be speaking to you today about what it's like to hack in 2013, especially using Pythonect and HackerShell. About 2.5 years ago, I've developed and released a programming language called Pythonect, which is essentially allowing you to do Dataflow programming on Python itself. And about a month ago, I've released a tool called HackerShell, which is essentially a Unix-like shell, but that lets you instrument all sorts of attacking tools together as if they were connected to each other. HackerShell is using Pythonect as a scripting engine. In this talk today, I will try to explain the motivation behind the development of these two projects and obviously the benefits for you guys to using it. So before we can dig into what exactly it means to hack like it's 2013, let's do a quick review about what's actually is hacking back in the days or what is hacking today. So essentially we have people writing scripts, pentesting script, malware analysis script, forensic scripts in all these different languages. It could be Ruby, Perl, Python. And then when people try to mingle these codes together, they have a difficulty. They either have to port it or rewrite it. So essentially, we have a low-code reuse because of that. Sometimes people would like to do a little bit of modification to perhaps address a specific protocol feature or a specific protocol modification. And many of these tools are written in a very straightforward, patchy way, which means that even the slightest change could cause a complete rewrite of the tool itself. So again, we're running into a low-code reuse problem. One of the biggest problems and one of the problems that I'm trying to tackle with HackerShell is that nowadays, most of the security tools are agnostic to each other. Anything from Nikto, Metasploit, Nmap, these tools can produce smart outputs. They can produce XML files, but almost none of them can import other files into them. So essentially, if you'd like to do a chain of these different tools together, you'll have to convert the information from each tool so the other tool can accept it. So that's the problem, the agnostic tools. Again, it also shows up with parameters. Most of these tools are command line parameters, and they use these different commands. There's different flags. So again, you'll have to tailor-made the scripts to call the tools using these very specific parameters. And the latest problem that I'll be tackling in this hacking like it's 2009 is the scalability issues. So nowadays, when we're going big with the cloud and the multiprocessing, people would like to use this computing power to do more, to take a problem and then apply it to as many computers as possible to solve it as quick as possible. Many of these tools are written in a very low-level languages such as C, C++. So essentially, for them to be multi-threaded, it has to be a feature. You have to code it in these tools. So some of these tools does offer a multi-threading or multi-processing capability, but on a high level, it's still something that's not been done, and you cannot instrument tools to run over a cloud just like that. So this is a very quick summary of the problems that I've encountered while trying to do pen testing and all this interesting stuff over the past 10 years. Now, if we are walking or trying to walk toward a red teaming or a bigger and much smarter pen test or engagement, then these problems should be solved as quick as possible, because while having these problems, it's very difficult to create a scenario or to reproduce a scenario which involves all these very different vectors. So agnostic tools, scalability, and code reuse is something that we should solve, and I'm trying to solve it in order to do hacking in a much simpler, faster, and efficient way. So taking all these bad issues or pain points and transforming them into features, what we actually would like to see is first synergy between different tools. So we would like to be able to take, well, almost any tool to run it and take the output and then plug it into the next tool and have the next tool extract this information, and we'll know exactly about the target, the host, and whichever parameters it will need to consume, it will find it in the previous output. Same thing goes for parameterize and parameters. We will not don't want to spend time trying to figure out how to troubleshoot these tools to work. We will just have them taking this information and process it correctly, so it will just run as we expected. We also like to maximize the code reuse. So if we're spending time writing a script or a program that does something, then this knowledge we'd like to encapsulate it and use it as often as possible. So if we have a function or a class or a component that does anything from a particular type of scanning to a particular malware analysis to anything, any process, any procedure that you guys are doing, then we would like to change it or to modify it every time. We just like these tools to be able to plug into this knowledge. Of course, if it makes sense and it's applicable, but we would like it to be able to plug into this knowledge and use it to either filter the output or generate input from it. And the latest issue, as I described, is the scalability. Nowadays that we have maybe a cluster, a few computers, something running in the clouds, we would like to be able to take all these tools, all this scenario, and just say, well, run it over this network. Use all these resources to do all these things. And of course, when it makes sense, do it in parallel. Run these things in parallel on different machines and get the procedure to be done as quickly as possible. So my vision is to Hacking like 2013 is basically the combination of the follow. So Pythonic, as I said, it's a programming language, which I'll explain in a few minutes, basically gets the power of Python and the Dataflow programming in it. And I'm using it as a scripting engine. And HackerShell is basically a platform that lets you take, plug in third-party security tools and metadata and combine them together. So essentially, you have a language, you have a framework that you can program, you can script that can take these third-party tools, create a metadata of them, and then instrument it the way you want to get into certain results or to verify certain assumptions. So let's get into the details. The first thing, the key ingredient for all this infrastructure to work was Pythonect. So as I said before, Pythonect is a Dataflow programming based on Python, written in Python. It's influenced mostly by the Unix shell scripting, Python itself, and then it's a bit of Perl. It's completely written in Python, so it should be running on any Python supporting platform, anything from a mobile to a supercomputer. It should run without much of a trouble. Pythonic has a website. You can feel free to browse into it. There's some documentation and, of course, instruction on how to download it. Since Pythonect is completely written in Python, there is no actual external dependencies that you're required to compile or to use. So as any other Python package, you can install it just as easy as using the easy install or the Python installer, and it will simply get it on your computer as fast as possible. The development of Pythonic taking place over Git, so you can also clone the Git repository. The Git repository contains the latest version, the unstable version, so you can gain the newest features as well as the newest bugs. So what is Dataflow programming, and why is it so essential into trying to do hacking or taking hacking into the next level? Well, there's many different types of programming and there's many different types of tasks. But if you look into how we are performing penetration testing, malware analysis, forensics, it's so easy to take a whiteboard and just describe the different steps, describe the flow of what needs to be done. So how come when we go to work and try to implement this flow, then we have to constantly trouble or trying to make the language understand the flow that we want? Well, this is very simple. Most of the languages out there, may it be C, C++, assembly, Python, Perl, are not Dataflow oriented. They're imperative programming. And therefore, we have to program in them completely different from the way that we can describe a flow. Now, Dataflow programming is more similar to the way that we can map ideas in our head. So essentially, a Dataflow programming is very fit to describe a penetration testing, a malware analysis procedure, or even forensics. Let's see a real life example. Let's say that we're tasked with writing this small program that will read a file, actually take a video from the file. we'll pass it to a video black and white frame processor and output to the screen. So we can describe this program into 3 major steps. We have the I/O, the reading the file from the system. We have the processing, where actually the information is being processed. The input is the information, and the output is a different information. And then we have the output of the system, which is the screen. So it's very easy to describe such process in a Dataflow way. Assuming that now we've been tasked with a different item, we've been asked to change the program from reading a local file to download the file from the web. So essentially, the 2-letter components, the 2-letter steps remain the same. We're still doing the video black and white processing, and we're still doing the screen output. The only step that actually has been changed is the first step, from the local file reader into the URL downloader. So assuming the URL downloader will download the file from the web, open it on the file system, and output, let's say, a byte stream, the program will remain working. So the information, the time that we spent encapsulating the knowledge for the screen output and the video black and white processing remains intact. This is a very good example of how code reuse works better in Dataflow programming. We simply break the process into components, and we only change the components that need to be changed. Most of the code will remain the same. Another very interesting feature, which goes to scalability, is the way that Dataflow actually is being working on the interpreter level. So the challenge in most low-level languages such as C, C++, Python, and Perl is that you have all these different functions, all these different tasks, but the interpreter, the compiler, does not actually know which task can be done in parallel and which cannot. So you actually, you as the programmer, you have to notify the compiler, you have to create this critical section when you're locking things or unlocking them in order for things to work in parallel in the best way. In Dataflow programming, every time that the flow is actually being forked or branched out into a couple of different components, we're essentially telling the interpreter, listen, this information is not blocking. You can use it for here, and you can use it for there at the same time. So actually, every time that we will have a branch or we will have a multiple choice for information to flow within the Dataflow program, we'll gain a multiprocessing or a multithreading. We'll see examples for it later on for free, without doing anything, without describing anything, simply because we're able to tell the interpreter that this information is not locking each other. It's not waiting. It can be spread in parallel. So just a quick rundown on the example. So here we've been tasked another task on the original program. Now they also ask us to write the file locally, not only output it into the video. So the program is essentially downloading the URL, the same component that we already wrote in the previous example, again using the video black and white frame processor, which is a component that exists from the first example, the screen output display, another component existing from the first example, and a new component called local file reader that essentially will take the stream that the video black and white frame processor generated and will write it to the file system. So the advantages of Dataflow programming are the following. We gain concurrency and parallelism just because the way we describe our programs, which apparently gives us the ability to scale when needed. Dataflow programs and networks are a very natural way to represent a process. So if you can go down to a whiteboard and describe what you're doing in your everyday job, or describe some tasks that you've been given, then most likely you can then transcribe it from the whiteboard into Dataflow programming as easy as that. And of course, as we've seen in the examples, taking components, replacing them, and integrating and merging, another components into them is very simple. Much more simpler than hard coding functions and replacing functions within other functions. Of course, it's not always perfect and there are some obstacles, but most of the obstacles, or perhaps the primary one, is actually the mindset. Programming, and most of the programming people that do software development are trained and taught to use imperative programming. They're trained and taught to use loops and ifs and all these different statements that may not have to exist in Dataflow programming, and we'll see examples for it right up. But the mindset is the most biggest obstacle for why people are not adopting Dataflow programming. And also there's the issue of the performance. it's worthwhile saying that Dataflow programming is not the language to write how things work. C, C++, Perl, Python, these are the languages that's best suited to write how things work. Dataflow languages is best to describe how things are connected to each other. So if you have these different components and you have this different software, a Dataflow programming language will be the best way to help them all talk together and create a bigger picture. But probably not be the best way to write the actual software or the actual how-to in it. Dataflow programming has been existed. Some say that even from the first CPU that ever existed, Dataflow programming was one of the languages that was proposed at that time. If you guys are doing or did any Excel, smart Excel formulas, then you essentially did the Dataflow programming. So every spreadsheet is capable of doing Dataflow programming, taking different values from different cells and add them or divide them or do whatnot is essentially a Dataflow that's describing the information. Hardware design languages such as VHDL and Verilog are essentially our Dataflow languages because that's how hardware actually works. It works in a Dataflow manner. Xproc, an open source language to transform XMLs one to another, is also a Dataflow language. Multimedia programs such as Max, MSP, composing videos, music, and other multimedia are actually using Dataflow languages to describe the video or the output. And there's a few other examples, but less notorious. So up until now, we kind of like talked about the theory and the different things that can or cannot be done in Dataflow, and we've seen these theoretical examples. It's time to see a little bit more hands-on code. So this is essentially the very simple program that you can write in Pythonect. This is the hello world program. So what we can see over here is that we have a literal, we have a string, the hello world, and then we have an operator, which I'll describe in the next slides, and then we have a function. So essentially, the string goes into the function, and the result is the string has been printed. I've customized the print function to also output an extra metadata, which is which process in the computer actually output the information and which thread in the process done that. We'll see later on that this information makes sense because as we will try to do, and our programs will become more and more complicated or more and more scalable, then it will be important to keep track of which thread does which job. In this example, it's pretty much a single thread application. There is only one flow that's existing, so there is only one thread participating in it. Okay, so while most languages are using operators to describe anything from mathematical actions into customized operators overloading, Pythonect is actually using the operators to describe how information will travel within the flow. So it's important to understand that while single-thread programs, the information can only flow in one way, or the order of information does not actually change anything, while going into multithreading and multiprocessing, the order of the information can change. So for instance, if you have a program that takes 3 different data sets and performs some function of them, an accumulative function that's perhaps storing the previous result and does something before that, then we would like the data sets processing to happen in a certain order. So then we have to introduce an operator that actually says, okay, this function have 3 different data sets, and we would like data sets to travel in the network within a certain order. For this, we have the pipe. The pipe is actually a blocking operator, which only allows one single data in the order of the first come, first output, first come, first out, to travel within the flow. And we will see an example for it later on. But right now, as a very simple idea, if we want to have a program that counts from 1 to 9, and we would like it to count in this order, then the pipe operator should be introduced before the print, so the numbers will arrive and printed in the same order they went out. The default operator, and the one that you'll probably end up using the most, is the non-blocking forward operator, which basically means any available information, once it's arrived to the system, will be output to the next component. This is practically very useful because if in the end component, it will essentially write into a database or do any other action to store the information for you, then the whole program can be non-blocking, and only the last part, the last mile, should be the one that will do the waiting. So as described before, the hello world is just a Python literal, as most languages offer, and print is just a function, a normal Python functions. There's nothing particularly special about it, and that's also part of the Pythonect advantage. It can instrument any Python code. It does not require any porting, any rewriting. Any Python framework out there can be instrumented in Pythonect in a Dataflow manner. So I've discussed a lot about the scalability and how important it is. So here's an example, a very quick example of how you can do actually a multi-threading in Pythonect. So as opposed to the previous example, when we had the hello world string going into a single function, in this example, we actually have the hello world string going into a list of multiple items to print functions. So essentially, in Pythonect, whenever the destination component is not a discrete, it's a list, a tuple, or anything that has more than one, then Pythonect takes this advantage and then create a multi-threading application by default. So, as you can see, the output of this program was actually printed hello world twice. As I said, it's a multi-thread program. And on the bottom, you can see that there's two different threads that has been participated, thread number 4 and thread number 6. So this is how easy it is to actually scale a program in Pythonect. All you have to do is take the functions, take the steps that you require, and put them within a list or a tuple, and there you go. You have a multi-thread application right there. Just to emphasize the point of Dataflow programming, in most languages, in order to print a hello world twice, it will be two separate lines of print hello world and print hello world. But in a Dataflow programming, this is actually useless because we already have the string as information on the flow. So if you would like to have a single thread programming that's displaying a hello world twice, all you really have to do is just pipe print again. And you will have it printed twice. So this is the kind of thinking that is separated from imperative programming. You always have information on the flow. You always have something waiting, and you can pass it to another function or another step, and it can reuse the information and do more actions on it. In this case, print simply takes the information, prints it, and passes it as it is to the next component. But of course, it can do anything from changing it, appending it, whatever. It's not only the second step in the flow is capable of doing a multi-threading. Sometimes it makes sense to start the actual program or script from a separate or a number of data sets. So for instance, anything from multiple IPs into multiple malware binaries, all these can be used as a starting point for a specific script. So in the previous example, I've showed you how we take a literal and expand it into a multi-thread program. In this slide, you can see that I'm doing the reverse way. I'm having the beginning of the application is actually a list with two different literals in it, the hello world, and print is actually the single component. The result of this, script is much like the others. It will print hello world twice from two different threads. In this example, 9 and 10. So there's a lot of flexibility in the way that you can manipulate the flows and scale them. It's also worth telling that even it doesn't have to be a compile time feature, so you don't have to specify a list every time that you actually want to expand the flow. If a function returns a list in runtime, then the Pythonic interpreter will interpret the return value as this function has created a mini flow with all these possible options. Let's take the information, pass it to them, and create a multi-thread application at the spot. So essentially, you can also, depending on the functions, depending on the way that you're using them, you can create and scale in runtime. So a quick overview of the syntax. As I said, currently Pythonic is a very minimalistic. Designing a programming language is more than an art and a science. My personal take on this philosophy is that I'm trying to keep the language as abstract, as minimalist as possible, giving the programmer and the runtime as much power as possible. So currently Pythonect has only three symbols, 2 operators, the arrow and the pipe. One is the non-blocking forward and the other is the blocking forward. And underscore is basically using as a way to reference the information on the flow. So if we're taking the previous example, and let's say that I'd like in the next step to add an RVAsec into it. So all I have essentially to do is just reference the flow using the underscore, and then I will create an expression which will evaluate it into 2 strings connected together, and we have it. It's not only limited into strings. Obviously, it can be done using any type of objects that this makes sense to do actions on them. And of course, in much complex systems, it can also represent a class, an instance, a method. So there is no actual limitation to what can be done using the underscore. OK, so moving on with the talk, now we will try to address some simple, very simple security tasks and see how it can be automated using Pythonect, only Pythonect. So this is a very simple Rot 13 encrypt and decrypt program. Again, it's nothing really famous. Python does allow it out of the box. This program essentially takes an input from the user and pass it to a Rot 13 function. And the first time it will encrypt it and result in the encrypted text output. And the second time entering the encrypted text will result in decrypting it. So just a quick example of how it's actually working. We've taken the program, so the text will be hello world. This will be the encrypted example of it, and running the program again with this text. Sorry, this text as an input will decrypt it back. So it's not much of a useful program, but then again, it goes to show that encrypting and decrypting, testing strings and different permutation is something that's very fitting into Dataflow programming. A network example is actually the following. Again, a very simple example just to show that also doing networking tests is essentially a flow of actions. So in this example, you can see that I'm utilizing the FTP-lib package, which is a part of the Python standard library. And what I'm doing is I'm passing this string ftp.gnu.org into the FTP-lib package. And what happens is that I'm invoking the login function, the login method. And if the login method, it's a true or false function. If it returns the true, it will go up in printing this FTP is essentially allowing anonymous login into it. And if not, this text won't be printed. So the reason I'm giving up this example is because it shows some interesting aspects in Dataflow programming. So essentially, the flow should contain meaningful information to process. Passing true or false values are essentially meaningless because it's just saying 1 or 0. So I've taken the liberty and I've taken these, all the functions or all the expressions that are evaluated into true or false, and I'm kind of using them in order to indicate whether there is a meaning to continue with the flow or not. So in this particular example, as I said, I'm using the FTP-lib class to initiate an FTP class. And then I'm invoking the login method on this particular class. Now, as I said, the login method can only return true or false, depending if whether it's successfully connected to the FTP site or not. If it's successfully connected to the FTP site, then it will return a true. And then the Pythonect program will essentially continue with the flow using the previous value that has been entered. So in that case, it will be the ftp.gnu.org string. Now, if the login method has returned false, which means it was not able to connect to the FTP site, then Pythonect will terminate the flow at that point. So the print allow anonymous will actually never be executed. So it's not limited to specific functions. It's not limited into anything. It's just a way that I'm treating a true or false examples values in Pythonect. Going into a little bit more elaborate example, this is an example for a very simple command line fuzzer. So essentially what we're looking over here is the following. First, we define all the possible, or in this case, a very limited char set, but we define a number of characters that we would like to use as an input buffers into the fuzzer. The second line describes a nested loop. We'll take each character and multiply it by these different sizes. So essentially, if we look in the program, we will have the %s as a character, and then it will be multiplied by these values, creating a big buffer. And this big buffer will essentially be passed, in this example, into -bin-ping as a command argument. So if there is, in this essential testing, if there is a format string or a buffer overflow, then this very three lines sample will find them. Running it, again, as I said, is as simple as that. We have the first line describing all the possible characters. Of course, it can be more elaborated and more characters can be inserted. The second line, creating the buffer on the fly using these sizes. Of course, more sizes can be entered and elaborated functions can be used to calculate it. And the last line is just trying to execute ping with this output. So it's pretty much going to flood my screen right now, but just to give the idea, this is what it's going to do. It will try all these different characters, all these different variation depending on the characters and on their size. Of course, it's a very simple fuzzer and much more can be built on top of it and much more can be built using this way, just to show you an example. There's more examples, and I've been, as I said, I've been trying to take Pythonect and try it on different domain problems on different realms. So I've did anything from scraping LinkedIn profiles into building all these different fuzzers and trying to do also static malware analysis using Pythonect. So you can visit my blog and check these posts for more examples or more advanced examples. And this cool guy called Lightbulb1, actually, he picked up on one of my blogs, and he actually implemented some of the fuzzers that I actually wrote on his iOS, on his iPhone. He actually found a buffer overflow or some sort of vulnerability in his iPhone, and he describes how he did it in his blog. So if you guys want to check it out, again, it's in the presentation. Feel free to browse and look on the examples. So this was the first part of the talk, and it's mainly just to introduce you the Pythonect and its capabilities and what you can do with it. Now, in the second part, this is actually my end game, and it's exactly what I want to show you guys. So as I said before, one of the problems that we've described in what is doing hacking nowadays is all the agnostics tools, the low-code reuse, and the scalability issues. I try to solve them using basically going as upper in the tree as I can into creating a shell which is resembling the Unix-like shell, but also gives you some built-in features and built-in commands, so you can actually instrument in it scripts, or one-liner scripts or more, that will be taking you much more work using just a simple Unix shell or whichever variation of it that you like. So the idea is a shell, it's a command interpreter with a Pythonect. Pythonect is a scripting engine. So basically, you can script Pythonect within the shell, and you have already made component library using these many different tools. I'll describe them in a bit. I'm constantly working on adding more support for more tools. Currently, it's a bit limited, but the idea is very shown. So you can see what it is today, and in the future, it will be much more elaborated. Again, it's an open source project influenced by the Unix shell scripting and Pythonect. Again, it's completely written in Python, so it should work from anything from a mobile into a supercomputer. You can visit the website. There is not much of documentation right now on it. I'm constantly working on adding more documentation, more examples. But there's a few nice examples there, and of course, all the ways that you can install it. So as I said, a few words, written completely in Python, hosted in GitHub, much like Pythonect. Feel free to clone the repository or using the installer. So the motivation for everything, as for everything in the motivation, is to take over the world. I failed, bummer. And then I moved on into trying to do something more useful out of it, which is, as I said before, trying to automate security tasks and reusing code as much as possible, basically creating a framework where then I can go on and try to do red teaming or more advanced examples while I have the basics already locked in and working for me out of the box. So installing HackerShell, much like installing Pythonect, is a very simple process. Just type is install or pipe on your Linux, Windows, or Mac, and you should pretty much be set by now. It's important to emphasize that this is only installing the HackerShell. The HackerShell is also dependent on third parties, which is basically the tools that it's trying to instrument, may it be Nmap or W3AF. So this will not install all these tools on your computer, it will just get the shell into it. I strongly recommend using anything from Pen2 to Backtrack and install HackerShell on these distros. Then you will have all the utilities already installed and HackerShell will be able to instrument them. So you won't have to go through the pain of installing everything on your laptop. But then again, if you want to do it, it's possible. There is no actual limitation here. Okay, so as I said, a little bit in the contrast to what I described before, this is a component-based software engineering. So it's also a data flow, but the idea here that we have components, and all these components share a similar context. I'll go into details much further. We have external components, anything from Nmap, W3F, TNSDIC, Nikto. They're all been currently supported, and if you have them installed, HackerShell will be able to instrument them out of the box. As opposed to it, there's also internal components, which are one implemented within HackerShell, and these are more guiding components to help you describe the flow better, so the rest of the flow will group in the way that you like. So you have components that will take strings and convert them to URL, IPv4 addresses, IPv6 addresses, and etc. So here you can see two quick examples and just a little bit of a background about how these are being played with being components. So first of all, there is a lot of automatically stuff happening in HackerShell to get all these things working together. But this automagic can be also broken down and be customized. So for instance, in this first example, we can see a very clear, very simple scanning script. So we have the local host into the host name and then into Nmap. Now, if you would like to add a customized Nmap flag into the script or into the actual execution, then it's not a problem. You can simply add it as a constructor to the component, and you can use it to pass any parameters that you would like to customize Nmap to run as you want. If you won't pass any parameters, I do supply default. Each component supplies a default set of running parameters, so it should work. But then again, maybe not to your taste. The second one is describing the way that I let you to debug the actual output. So as I said, the information is well kept within the flow. I'm constantly trying to take the outputs of every tool and convert it into this major metadata structure, which I'll show in a few slides. But if you would like to have the raw information being displayed, that's not a problem. All you have to do is supply the debug value into the component, and the actual output will be printed to the screen. It can be attached to almost any component out there that this makes sense for its output to be displayed. Obviously, URL and all these internal components don't support it. There is not much to display from these functions. So as I said, one of the automagic things that happens in HackerShell is the context. It's basically each component, when it's executing the application, whether it's internal or external, the output is a context, which is basically a metadata structure, a very abstract one, which is I'm using a dictionary assistive array to represent it. And this context can contain anything from what's the IP address that we start with, the scan, what's the current flow, what other tools found, and etc. So basically, every component is programmed to accept this context structure, both as an input and as an output. And by normalizing all the components to speak with this metadata structure, I'm able to do very interesting things. So this is an example of how actually the context allows you to change the flow of the application without worrying about it being piped in the correct order or it's being piped in the correct sequence. So as opposed to a pure data flow programming, it wouldn't make sense in that sense to have ping after an Nmap, because if we look on the very pure basic data flow way, then ping should consume the actual target. But since, as I said, all the components are passing the context, and the context does contain the source or the target URL, then you can place them not to represent the actual flow of the program, but more of the mindset of what you like things to happen and with what order. So in the first example, what we have here is basically we're taking the local host as a target, converting it into a URL, running nmap on it, and then pinging it. So if there is anything else further down the ping, then the question will be, if the host is not pingable, then the rest of the actions won't take place. So basically, ping is acting as a filter component in this example, but it will only happen after nmap has been executed. In the latter example, you can see it's pretty much the same, except the ping in the nmap order is reversed. So what we have here is that ping, basically the program will say that only if the URL is pingable, then we will proceed into port scanning it. Either way, the power of the context is it's been able to pipe it in at every level and at every step. So as I said, you can change it to fit what you would like to have. Another big feature of the context in Pythonect is that this has actually been, you're able to touch it and program it in runtime as easy as that. So this is a very, very simple pen testing script right here. We're taking a URL, a string, converting it into a URL, running nmap on it. Then we have this expression we'll discuss in a minute. And afterwards, we're putting it into W3AF. If you're not familiar with it, it's an automatic pen testing toolkit, and then printing the result. So essentially what we have in this expression is a way for us to say that, okay, not all the flows should always be automatically executed. If you would like to specify conditions, specific conditions into running the certain flow, then we're able to do it describing a very simple language using and or not, such as in Python expression, and accessing the actual context values and compare them. So in this particular example, I'm only interested in scanning, actually I'm only interested in conducting the pen test if nmap has resulted in finding a port 8080 and the service identifier on this port is HTTP. Anything that doesn't match this requirement will simply not proceed into the pen test. So essentially, you can use this expression, this context, to create all these different situation and variation of how you would like the pen test or the procedure to take place, depending on the information that has been populated in runtime. So from a 30-feet high-level diagram, this is how things look like usually when you're going to use HackerShell. So the first input will usually be a string, which will describe anything, any endpoint from an IPv address into a URL. And then you will use a root component, which will be the first step into HackerShell, and that will be how to describe this information in a context way. Is it a URL? Is it an IPv4 address? Is it an IPv6? Is it a local host? There's a library of different root components that allow you to take and customize the information based on what it actually is. And the root component will generate the initial context, and from there it will simply go into all these different components. So as a final example, I will show you a step-by-step web pen test script using HackerShell and the very few components currently being supported. So let's say that we're tasking to pen testing HackerShell website. Please don't. But having said that, we'll take the hackershell.org and we'll describe it as a domain, because we're interested to see in all the different subdomains that may result out of scanning it. So we're using the DNS dig tool to basically generate, to brute force and generate all the possible subdomains out of the hackershell.org domain. So the result will be the DNS.dig, the -4 command line is actually to generate IPv4 as opposed to IPv6. So it will generate any subdomain that has a valid IPv4 addresses result from them. So now that we have all these different domains, the first thing that we would like to do is essentially to scan them. So we're going to ask the DNS-dig every subdomain, every host name that it will find, it will then send to nmap, and Nmap will obviously port scan it and to see which services are running on it. The next step will be I'm going to plug Nikto into it. So I'm going to use Nikto as a web vulnerability scanner. So essentially, the flow will be taking the HackerShell.org, consider it as a domain, enumerate or brute force all the possible subdomains using the DNS dict, scanning all these different domains. And if any of these subdomains may have an open HTTP port, such as, for instance, the example will be www.hackershell.org, it will obviously have an open HTTP service. So if it will have an open HTTP service, Nikto will be able to automatically consume it. Nikto being a web service or web-oriented pen test tool, whichever HTTP service has been identified, it's able to consume. The context is valid for it. So simply it will take the Nmap context and run on it. And a step further will be to plug another web pen testing tool into it. So now that we already did a check on the web server surface, I'd also like to step in and do a more application-wise pen test. So in this example, again, I'll take down the flow top to the bottom. We have hackershell.org domain. We're brute forcing and using DNS dig to find all the subdomains. So, so the HackerShell is a string and converted into a domain. At this point, the context has been initially created. And every step, the valid context will be added more information to it. So in that sense, the DNS dict will create context based from the domain, all the possible subdomains that it's able to find. The Nmap will add the layer of the different services and ports found within each subdomain. Nikto will only consume, basically it will filter only the contexts that contain HTTP services. It's the only thing it's able to consume. So from that on, it will pass it to the W3AF tool, which will take the URL and the HTTP service information, construct a website or a URL from it, and will begin doing a pen testing. So the final step will be to actually add the reporting into all the equation. Essentially, all this information up until this point is actually encapsulated within the system. The print function, in this case, will do a very simple ASCII style report generation of all the different contexts that has been survived up to this point. So again, it will be only HTTP services because it's the only thing that Nikto and W3AF can consume. So essentially, we'll have all the different websites and all the different vulnerabilities that we've found in them. So just a very quick demonstration of how HackerShell looks like and feel like. So this is how HackerShell looks like, a little bit of an ASCII art over there to nostalgia. So essentially, as I said, it's a very Unix-like shell, just doing like these very simple things to quickly show you some output. So as I said, you can simply take information and plug it into and create all these different flows. Now, okay, that was not a very good example. But the thing is, if you're not explicitly trying to print the information, then HackerShell will try to generate some sort of an executive summary. So in this case, it will try to take all the meaningful context and just try to like place them in a tree structure like, so you can see. So in this example, I simply did an Nmap on my own computer, and I end up having this tree with all the different services that has been found on it. Now, I could have explicitly asked Nmap to print each and every context to have more information on it. So as you can see, for every port that has been found, it will create this properties structure, and there you can find the information that's related to this specific context. So as you can see, for instance, in this context, it's been found that I have an SSH service running on port 22 on TCP. The flow that has been taken to determine it is the IPv4 into Nmap. The target was my IP, and I'm using the IP in this context. So whichever tools can consume IPv4 address, they will be automatically fed using this information. Moving on, the vulnerabilities are also being processed and displayed when asked to. So in this example, I've just run Nikto on my own computer, and surprisingly enough, it found some stuff on it. So again, as I said, only the context that's been actually processed and survived using the different filters are being used. So I'm getting the sign here, so I'll be very quick about it. So this is the properties of only the HTTP because it only makes sense for Nikto. And this is the vulnerability table output, which is basically parsing all the Nikto's output into the table. Again, this is all part of the metadata, and it's all been possibly extractable and manageable and scriptable by you using HackerShell. You can go to the websites of both HackerShell and Pythonect to learn more about these languages and see more examples. Thank you.